So we now have our building block, which is stationarity, which we translated into moment stationarity, the mean, the variance, and the covariance, not depending on location. Then we move to a way to characterize the spatial characteristics of a continuous process, which was a little unusual in that it focused on the squares of the differences. It focused on the variance of the difference. But in the end, we saw that this was connected to the more traditional, if you wish, notion of a covariance, in that we had this relationship between the semi-variance, the variance, and the covariance. The important part about all of these is that they're indexed by distance. This h is actually distance and direction, but I've just made it simpler by using distance. But h is the separation, and we index this by the separation. In principle, the separation is continuous. In practice, it's not. And we group our observations in bins and then compute the estimates for those bins. So far, we just have our points. You know, for each of our bins, we have a dot. That's not going to help us. What the ultimate goal is spatial interpolation. We want to predict data where no data exists, for locations where we don't have measurement. Okay. I measure the temperature on all buildings except on the one across the quad. How do I get a temperature for that building? Well, I'll get it by exploiting the distance between that building and other buildings in the sample. So the key is to make a connection between the semi-variogram or the covariogram and its relation to distance. How does it change with distance? Because then once I know the distance, I just plug it in there and I get the covariance or I get the semi-variance for those two locations. So in other words, that gives me a handle on how that building correlates with this building once I know how far these two buildings are apart. And that's where the models come in, because they're theoretical ways of characterizing that relationship. Just like we have, to get our bell shape, we have the equation that we use to get the bell shape. Here we'll get an equation that we'll use to get a theoretical model for the variogram or the semi-variogram. And we will use the estimates of the semi-variogram that we compute from the data to fit a theoretical model to that. And then once we have a theoretical model, and say I have my distance, I plug it in the formula, and I get my covariance or I get my semi-variance. And that's the way it works.
So that distance to predict temperature, we have a formula that predicts how distance relates to temperature.
No, we have a formula that relates how temperature at two locations, the correlation between temperature at two locations is related to the distance between the two locations. So if I know how far this building is from the current building, I know something about the correlation between their temperatures. Remember, it's the second moment. It's not the first moment. It doesn't tell me what the temperature is unless I have a model for the mean, right? So I need that too. And when we talk about Kriging, which is spatial interpolation, that's a big part of it. People tend to forget this. There's all this focus on correlation, but correlation doesn't tell you anything about the mean. It's a second moment. And the point of this correlation is to make the predictions more precise. So for all practical purposes, on average, they're the same. On average. But the second moment is how your prediction varies around that average. That's where all the action is in the geostatistics. Okay? So you don't know anything about the mean in that building, but you do know how it's correlated with the mean here. And so that is the way you get at it. Okay, I won't have time probably to cover all of this, and I don't want to start racing. So maybe I could cover some of the basic concepts, and then Thursday I'll just start by finishing it up and show you the two main theoretical models. There's many more. I mean, there's like 5 or 6 that are used routinely, but I'll just focus on 2. And if this is what you want to do for your final project, you're more than welcome to explore some of the others. You know, as in all these things, once you have the mechanics down for one, you have them down for all of them, so it doesn't really matter. What we're trying to do is think of what are meaningful parameters to characterize the semi-variogram. It's like put yourself in the place of trying to characterize this equation for the bell shape. Okay, what are meaningful characteristics? Well, the mean and the standard deviation, and then we can draw our bell shape. Now, similarly, we want to get meaningful characteristics for a semi-variogram. What is something that is a meaningful property of that statistic, which is a statistic that tells us something about the square differences as they change with distance? Well, we'll focus on distance. What happens to these square differences either as the distance gets very large or as the distance gets very small? Okay. Let's go to the large first. So what happens as the distance gets very large? At some point we said these places have to become uncorrelated. What does that mean? That means that if we move, say, from 20 miles to 25 miles, there's no more increase of the square differences. They're uncorrelated, so it doesn't change anymore. So at that point, the part of the covariance, the correlation, if you wish, between 2 points that has to do with the distance disappears. As we said before, for all practical purposes, they become uncorrelated. For all practical purposes, C of H becomes 0. So if C of H becomes 0, what is a semi-variogram? It becomes the variance of the process. This variance is called the SIL of the process. As I mentioned before, geostatistics doesn't come out of statistics, it comes out of engineering, and they have different words for everything. So rather than calling this the variance like everybody else would, they call it the SIL of the process. And we'll refine that a little bit later on. There's a difference between the SIL and the partial SIL. That's important for you to know when you interpret the results of a model. But for our purposes right now, it's very simple. You know, you look at this equation here. If the second part goes to 0, if the covariance goes to 0, all you're left with is the variance. So at that point, the average square differences, or half of the average square differences between random variables, that and further distances apart, equals the variance of the process. So that's the same thing. So this gives you a way to estimate the variance. You just make sure the points are far enough apart and estimate a semi-variogram for those distances. That value is an estimate of the variance, which is a different way from what we're used to. What we're used to is, get the average, get the mean, then get the square deviations and take the average of those, right? We don't need to do that. We just do the variogram. If we do it for points that are far enough apart, the estimate of the semi-variogram will in fact be the variance of the process. Let's flip this around. And let's say, okay, now we know that if we go far enough apart, we get the variance of the process. Now, where does this kick in? At what point do we get CH to be 0, effectively 0? For what H, for what distance range do we get that there's no more spatial autocorrelation? This distance H is called the range of the process. That's a very practical notion. In a lot of processes, you're interested in spatial autocorrelation because you don't want to have any. And so this gives you an answer. As long as I stay H distance enough away, the range of the process, there is no longer any spatial autocorrelation. So then for all practical purposes, I have an uncorrelated sample. So if I want to avoid problems with spatial autocorrelation, this is one solution. The solution is sample observations far enough apart. Now, how far? That's the range of the process. That's a characteristic of the spatial process. Of course, unless you know this ahead of time, it doesn't help you. Right? So in practice, you can't just say, I'm taking 20 miles. The 20 miles is going to have to come from an estimation process where you use data for pilot data or a pilot sample to try to get a handle on what the range is, and then you can do your real sample and use that to get locations that are far enough apart. So the range is a second important characteristic of the process. So we have the CIL, which is basically the variance of the process. We have the range, which is a distance beyond which there is no spatial autocorrelation. And then we have a third characteristic that I'll talk about in a second. So this illustrates conceptually, in a theoretical process, the variability of the square difference is continuous with distance. So we see we start at 0, this goes up until we reach a certain level, and then beyond that it's flat. This height is the variance of the process. That is C0, because at this point there is no more spatial autocorrelation. So CH is 0. Where does this kick in? Here, at this distance. This is H. This is the range of the process. So in this stylized process, where we have that the semi-variance keeps increasing with distance up to a point, and then it becomes flat, the height of the flat part is the CIL, or the variance of the process. The distance from the origin that you need for it to become flat is the range of the process. Those are two important characteristics. So you see where we're going, or maybe not. We're going to these models for a variogram that will be stylized functions like this one of how the variogram or the semi-variogram changes with distance, and we'll have parameters that plug into these formulas that will be related to the range and to the variance or the CIL of the process. There's one more. You see this comes out of mining, which is called the Nugget. And so far we've been focusing on the part on the far end where H increases. The Nugget has to do with the low end where H goes to 0. Now, as we saw by definition, at 0, the semi-variogram should be 0. Okay, you start at the origin of the process. At distance 0, it's C0 minus C0, that is 0, right? So we start at 0. What if it's not 0? And the reason this what if is actually because in most practical circumstances, it is non-zero. How do we explain this? There's two interpretations. One is simply measurement error. Okay, remember our bins. Okay, we're putting the pairs of distances in our bins. We say we have a bin from 0 to 2. But what if the closest houses are a mile apart? I mean, a 1 unit distance apart. We have no information whatsoever about what's happening at the shortest distances. Distances shorter than the shortest distance that we observe. So there we're flying blind, which is a measurement error. So we're actually trying to fit a curve without having observations in a range of the curve that is relevant. And so we don't have anything there, so that's measurement error. Another interpretation, and the one that was more interesting from a mining point of view, is that there's actually two scales of variability. One is the overall scale of variability, which is what we're getting with our semi-variogram. The other is one that happens at a much smaller scale. And this is where the notion of a nugget comes from. This is gold mining. Geostatistics was started out in South Africa in gold mines. So a nugget is a good thing, right? So you're trying to find out if there are clumps of gold that have higher variability than they should be according to the process. And so, in other words, this is a violation of one of our assumptions, because we've been saying the process has to be the same everywhere. So how do we deal with this? We say, well, it's not one process, it's two processes. One process at one scale, which is the nice, smooth semi-variogram, and then another process as a much smaller scale that we don't really observe the intricacies of the correlations for it, but we see that there is additional variability, which gives us a non-zero variability at distance 0. So at very small distances, this is our nuggets, our clumps, there is more variability than there should be. And so this is going to shift our curve up. And that's basically what it boils down to. I'll show it to you in the lab. It's in the theoretical part. But basically, we have an intercept, if you wish, which is now the nugget. And then we have the variogram that goes up to the sill. And so the total of these two variabilities, the nugget plus the rest, is called the sill. The difference between the sill and the nugget is called the partial sill. And we'll elaborate on that in the lab. But basically where I want to close is that we now have these characteristics of the semi-variogram, and we'll plug them into theoretical models. Now, these theoretical models have to be legit in the following sense. You don't want a model that gives you negative variances. Now, we're dealing not with variances, we're dealing with a multivariate concept. As I said, the covariance matrix, that is an n by n matrix that has to be the equivalent of a positive variance, which is for matrix algebra, positive definite. So in order for that matrix, that variance-covariance matrix between all the pairs of observations to have proper values, the function that we assume for the covariance of points that are a given distance apart has to give us the right numbers. It can't give us numbers that give a variance-covariance matrix that is singular or negative definite. So this puts constraints on the kinds of equations or formulas, if you wish, that we can use. This is, in a nutshell, what this boils down to. It has to be positive definite for the variogram, for the co-variogram, sorry, negative definite for the variogram. Isotropic models are the same in all directions. Non-isotropic models have directional effects, which mean that the h is not just distance, but it's also direction, and we'll deal with that in the labs. And so we're moving from, it's really a three-step process. We start with the variogram cloud plot, which is everything. All the pairs and their square differences plotted against distance. Then we simplify that. We go to distance bands, and in each band we get an estimate, our semi-variogram estimate. And then we have to go back to something that is continuous with distance so that we can use it for prediction purposes. The reason we want a model is we want to plug in a distance, and then the model will tell us what the covariance is for two locations that are that distance apart. That's the whole purpose. So these models, these variogram models, they have to be proper, or as it's referred to in the literature, they have to be valid. Now, this is kind of a formal mathematical requirement, but the intuition is very simple. Just like if you're going to specify a variance, you can't come up with a value of -5. It doesn't exist. So here we have the counterpart of that, which of course is multivariate, so that it doesn't pertain to a single parameter like a variance, but it pertains to the whole variance-covariance matrix. So not only the variances at each location, but also the covariances between every pair of observations. That matrix has to be valid in the same sense as a variance has to be positive. That matrix has to be positive definite. So the covariance of the process, which we've called C of H as a function of distance, has to be valid, and to be valid, it has to be positive definite at every possible distance. So this CH has to be positive. Then it's a little, I mean, it's not complicated to show this mathematically. It's a little difficult to get the intuition of it. It's the other way around for the semi-variogram. So the covariance has to be positive definite. The semi-variance has to be negative definite. One easy way to remember is that they're flip side of each other. As we saw last week, the variogram goes up with distance. The covariogram goes down with distance. Think of correlation, Tobler's law. As you move further away, the correlation goes down. With the variogram, as you move further away, you get closer and closer to the actual variance of the process, which is the set, which is the limit. So these are formal mathematical requirements that any function that you want to use as a model for the variogram has to satisfy. Then we have some other distinctions between different types of models. And we've already talked about this a little bit. The difference between a model without and with directional effects. An isotropic model is just a single equation, one that is only a function of h, which is distance, no direction. Then in directional variograms, we get a different equation with possibly different parameter values for different direction ranges, like 0 to 45, 45 to 90. These would be each a separate equation. All the equations together are the model for the process. And there's some formal requirements of when you can do this. Basically, it's an additive reasoning that you add up the different pieces of the variance from the pieces that are associated with different directions, and or different directions and distance bands, I should say. So it's basically a decomposition of the variance of the process into parts that are due to particular directional effects as well as the overall effect. We won't get into that except just for the sake of the exercise. We'll basically be focusing on isotropic models. Those are, in any case, the building blocks, because the directional ones are simply isotropic ones restricted to a particular angle of interaction. And so within that angle, 0 to 45, for example, they are, again, isotropic. Only thing that matters within the angle is the distance. That's what that is. So there's lots of these. And just to give you an idea, I'm listing 6 of them here: spherical, exponential, Gaussian, power, Matern, and whole. Or some of these are monotonously increasing or with distance. Others have these kind of wave effects to show distance bands where you have alternations between positive and negative autocorrelation. This is a little more complicated. All of these basically boil down to an equation. And let me just give you 2 examples, which are the workhorses in practice, or at least the textbook practice. In real practice, you often have to resort to these more complicated models, depending on what it is that you are modeling. But the one that is what I call the classical theoretical variogram, it's called the spherical variogram because it has this nice classic shape. That's the one I've used to illustrate the concept of a sill and a range. It follows, it's basically consists of 2 parts. One part that works between the origin and where you reach the range. So that's the curved part. And then the other part, which the semi-variogram equal to for distances larger than the range? It's the variance of the process. It's the sill. It's flat. So you have two parts to this function. Let's do the second one first. For h larger than a, where a is the range, the semi-variogram is a constant. And this constant is the sill. And in terms of specific parameters of this model, that consists of the nugget, C0, and the partial sill. Now this is a little bit confusing. When people refer to the sill, you have to make sure which one it is that they're referring to, because the sill as a total variance of the process is the sum of these two parts. If there is no nugget, then there's no distinction. Then the sill and the partial sill are the same thing. But if there is a nugget, then you start a little above zero. So then the sill is actually that little part that you get at zero, the nugget, plus from there to the actual sill, and that difference is called the partial sill. And in terms of estimating the function, you have to separate these out, because the sill is like an intercept, if you wish. And then the nugget is like an intercept. And then the partial sill gives you an idea of the curvature of the semi-variogram. In fact, how high is it going before it becomes flat? That is the idea. So beyond the range, we're flat. Before the range, we have this particular shape, which is a function, a nonlinear function. See the 3/3 power here, of distance, which is the argument in here, and then this unknown parameter a, which is the range. So we have to think of our cloud plot or our semi-variogram. We have to fit this nice curve through those points such that we determine the three parameters. This is an example of a zero nugget. So the sill is the part where it becomes horizontal. The range is the distance beyond which it is horizontal. And the point is then becomes, how do we get the parameter of the sill and the range to fit this particular curve to them. Okay, that's what you do when you fit a model. The second model, which is a little bit different, because it doesn't have a finite range in a sense. It's an exponential variogram which just keeps on going. It keeps on increasing, but in the limit it reaches the sill. So it's more or less horizontal, but not totally horizontal. And that has also a notion of a range, but the range is not the same thing as in the spherical because it's not finite. The range is conceptually infinite, so then that's not useful as a range, and people use 90% of the asymptotic range as the practical range, which is where for all practical, beyond which for all practical purposes there is no spatial autocorrelation anymore. So that is the concept here. And this one looks a little rounder, and you see, I mean, this is stylized, of course. It doesn't actually reach the range, but it gets there eventually in the limit. So 95% of this is called the practical range. And that's good enough because the increases that you get once you're beyond here are very, very small. So then, for all practical purposes, there is no real spatial autocorrelation beyond that. So this gives us two models that we will be working with in the lab. Then how do we get these parameters? How do we get the nugget, the sill, and the range? It's not that straightforward. First of all, we have a choice. Do we use all the pairs, or do we use the summaries of all the pairs in the form of the semi-variogram? And both of these are used in practice. And in fact, we'll see in the lab, some software uses, I should say, a subset of all the pairs to fit the curve. Other software, which is more of a purist geostatistical approach, uses the semi-variogram estimates. as we saw in the lab, that's not very many observations. That's, 9, 10 points through which you fit this curve, as opposed to if you use the variogram cloud plot, you probably have thousands of points to fit the curve. So there's a difference there. And as I mentioned before, geostatistics comes out of engineering, mining engineering, and that's very practical. So there are a lot of ad hoc rules to fit theoretical variograms to the data. These are rules that are not necessarily based on statistical consideration. In fact, you will see the eyeball method, fitting by eye, still fairly common in practice. And in fact, some software doesn't do any statistical fitting, but it lets you adjust the parameters and then kind of judge. They say by eye, but there's summary measures of fit, so you can actually compare the fit. But essentially, have you do the interaction of trying to find these parameters. More statistical methods are based on least squares, weighted least squares. The weighting is because, if you think of it, each semi-variogram is based on the pairs in a given band, and those are different magnitudes. So because they are different, the precision of your estimate will be different. And in econometric terminology, that's called heteroscedasticity. The variance is not constant. So whenever the variance is not constant, you use a weighted regression because you downweight the ones that have a higher variance. So the more precise ones count more than the less precise ones. That's the rationale behind it. So most software that fits variograms uses some form of weighted estimation, weighted least squares, and weighted nonlinear least squares. There's still some eyeball things out there. I'll show you one in a minute. The other thing that's important when you do this estimation is that you end up with parameter values that give you a model that is a valid model. And you may say, well, why wouldn't it be valid? Well, the data don't always cooperate. And we've already seen, or have begun to see, that there are a number of things that you can manipulate in this process. You can change the number of bins, you can change the width of the bin, you can change your distance cut off. Is it half of the maximum? Is it a third of the diagonal of the bounding box, etc. So all these things can be manipulated, if you wish, and so you might end up with nonsensical results. So you have to make sure that the results that you come up with for the parameters are actually legit in the sense that I just described for these valid models, that they are positive definite, that the covariance matrix is positive definite, and so on. Because you don't want to have any negative variances. And let me just illustrate this. We'll actually be using different software in the lab, but this is something that's been around for a while. It's VarioWin. And essentially what you do is you have, these are your observations, these points from the variogram, and then you fit. You set the range, you fit the model, you set the range, you set the sill, and you set whether it's directional or not. In this case, there's no directional effects. You set the nugget, and then you go, and it fits this curve. And you change these numbers, push the button, and it fits another curve. And then basically what you're doing is moving this up and down. This is the sill. And moving this connection point in or out. This is the range. And then you might have a little intercept here that is the nugget. So by manipulating these three things, you can fit different curves through these points. And then if you use some measure of fit, then you can decide which one fits the best. That's the idea behind fitting in VarioWin. What we will be doing in the lab is using a statistical approach, weighted least squares, and both in GStat and the geostatistical analyst use a curve fitting method, not the eyeball method. This is the same data but using an exponential variogram. So you see again, you manipulate the nugget here, you manipulate this up and down, and then you stretch the curve by manipulating the range. So that is a very practical method. It's been around for a while, and this is how you then get the parameters. So Once you have the parameters, the nugget, the range, and the sill, then you can plug them into this equation, in this case the exponential equation. You plug them in there, and then for any h, you get the semi-variance, or conversely the covariance, for points that are that distance apart. So now we're in business. Now we can do prediction, because all we need to get is this distance. We have the function, we have the parameters for the function, we plug in an h, and we get gamma h, or we get c of h, which is a covariogram. And then we can use that covariance to get better prediction at locations where we do not observe the data. And that process is called kriging. And that's what we're moving into next.